Good morning, good afternoon, or good night, everybody, depending on the time you're watching this video. In this video, I will go through the mechanisms involved in maintaining acid-base homeostasis in our body. According to the NMC curriculum, the competency attest in this lecture is covering under PI 6.7, which describes that the student should be able to know the processes involved in maintenance of normal pH, water and electrolyte balance of body fluids, and the derangement associated with this. And the learning objectives of this lecture are to understand the various homeostatic mechanisms which helps the body to maintain the body pH. Now, before we begin further, first let us understand the importance of maintaining the pH in the body. So, maintaining the pH balance is very important because it helps in the optimum functioning of the various biomolecules like enzymes, hormones, transport molecules, etc. Now, abnormality of pH in the body leads to conditions with serious health consequences like acidosis and alkalosis, which, if not treated in time, can be settled. So, in order to learn this concept, you will need to know about pH, acid, and bases. Acids are chemical substances that donate hydrogen ions, and bases are chemical substances that accept hydrogen ions. And pH is a concentration of free hydrogen ion solution. Now let's see the pH of various compartments in our body. For example, arterial blood has a pH in the range of 7.35 to 45. As we know, carbon dioxide is a volatile acid, and therefore venous blood has more carbon dioxide in comparison to arterial blood. So it is acidic and has a pH of around 7.35. Interstitial fluid, which bathes the body cell, has a pH of around 7.35, whereas the intracellular fluid has a pH of around 7, where the concentration of carbon dioxide is maximum, because as you know, it is generated here. So this place will be highly acidic as compared to the other places. Now, similarly, the pH of the gastric cavity is around 2, and that of the intestinal lumen is around 8, which is a little bit alkaline. Now, let's understand the concept of acid and bases further. So, acids are of two types. One is strong, the other is weak. Now, strong acids dissociates completely into hydrogen ion, for example, HCl, whereas the weak acids dissociates partially into hydrogen ion, for example, carbonic acid, lactic acid, which are found in our body. Similarly, bases are again of two types, strong and weak, and strong bases will completely dissociate into hydroxyl ions, sodium hydroxide, and weak bases will dissociate partially to hydroxyl ions, for example, bicarbonate. So please note that only weak bases are formed in our body. Now let's explore the various sources of acid in the body. So there are two types of sources. One is endogenous and the other is exogenous. So under endogenous sources for the acid, we have carbon dioxide. So carbon dioxide is transported from the tissues to the lungs. So the dissolved carbon dioxide produces carbonic acid, which is a volatile acid and acts as an acid source in the body. Next is the lactic acid, which is produced by the hypoxic muscle cell during exercise. During exercise, the lactic acid is produced under anaerobic condition. And similarly, keto acid is produced by the liver during metabolism is increase the production of glycols, and with the retention of carbon dioxide under a condition of hypoventilation, carbonic acid is produced. Similarly, in the condition of renal failure, hydrogen ions cannot be secreted in the urine and they are retained in the body and they serve as a source of acid in the body. Similarly, the exogenous sources are a person consumes in acid, for example, high protein foods and supplements. Similarly, with ingestion of acids, for example, salicylic acid, ammonium and before with infusion. So that can contribute with the exogenous source of acids. Next, various plasma electrolytes also acts as a weak acid at bases. For example, bicarbonate ion, phosphate ion, sulfate ion, they act as weak bases. And dihydrogen phosphate acts as both acts as weak acid. And the proteins can act as both acid and bases because they can accept the hydrogen ion and also donate the hydrogen. Now, let's understand what do we understand by acid-base balance. So, acid-base balance is the maintenance within a relatively narrow range of the hydrogen ion concentration with the extracellular fluid that is called as hydrogen homeostasis. Why do we need to have acid-base balance? Because many metabolic reactions, of course, all metabolic reactions in our body, they're highly sensitive to change in the pH, which do effects on the protein concentration and other biological activities, for example, the enzyme activity. So if we don't maintain the pH in the normal range, all these processes will not work efficiently and will cease to and will exist, and these can be very effective for the person. So, what are the ways in which the body pH in the normal range? So usually, there are three ways the body uses to keep the pH in the normal range. So these are the uh, chemical buffer systems, which acts within seconds. Then we have respiratory control, which acts within minutes, and this keeps a check on volatile acid like carbon dioxide, carbonic acid, and keep the carbonic acid content within the normal range. Then we have renal mechanism, which acts within days, and they take care of fixed acids and which are removed by the kidneys. For example, from carbohydrate metabolism, we have lactate; from fats, we have ketones; and from proteins, we have sulfate and phosphate. So these are removed by the kidneys over days and keep the level of fixed acid under check. Now, before we move further, let's see what do we mean by buffer. So buffers are chemicals which limit the change in the hydrogen concentration. When hydrogen ions are added or removed from the solution, when external hydrogen ions are added or removed, so these buffers will try to maintain the pH of the system. So all buffers are weak acids or bases. And you can imagine the buffer is like a sponge when hydrogen ions are in excess in the system. The sponge mops up extra hydrogen ions. And then there is a short supply of hydrogen. The sponge as a buffer can be squeezed out more hydrogen ion in the system so that the level of hydrogen ion and that is the pH remains in the normal range. Now, as I have told previously, there are three ways the body uses to keep the pH in normal range, in which the number one is the chemical pulse, which acts within seconds. So let's see these chemical buffers. So we have uh, carbonic acid bicarbonate buffer system, phosphate buffer system, protein buffers, for example, albumin, globulin, hemoglobin. So these chemical buffers actually seconds and they exist in dual conjugate acid and base pairs. For example, carbonic acid, bicarbonate double system has carbonic acid and bicarbonate. Phosphate double system has dihydrogen phosphate and hydrogen phosphate. And protein buffers have your side chains, which exhaust conjugate acid and base pairs. So let's further explore these buffers. First of all, is the bicarbonate buffer. So this is the main extracellular buffer contributing around 60% of the buffering action in plasma. So there is a physiological recognition of both the bicarbonic acid and bicarbonate component of this buffer. And as we know, the alkali reserve, that the alkali level is around 24 liter. Next, we also hear about one other component that is known as the buffer efficiency. So how efficient a buffer is. So it is the ability of the buffer to resist the change in its pH, buffer efficiency. And this efficiency is maximum over a pH range equal to pKa of plus minus 1 pH. pKa means that association constant, where uh, where the acid and the salt components are equal in concentration. So that is the pKa. That is also the pH at which the salt and the acid concentration are in equal amount. And from that pKa plus minus 1 pH, that is the range in which this buffer is having the maximum efficiency. Now let's see the phosphate buffer. So phosphoric acid is a polyprotoic acid with 3 pKa values. Means the 3 pKa values at 1.96, 6.8, and 12.4. So the pico of 6.8 over important to us. So sodium dihydrophosphate and disodium hydrogen phosphine conjugate pair makes the phosphate buffer. And it is the main intracellular buffer. So the ratio of the salt to acid is around 4, and the pK which we are interested in is 6.8. So this is the main intracellular buffer. Next, we have protein buffers. So proteins are electrolytes, and because of that, presence of the orbits. So histidine amino acid imidazole group has an pKa when move around 6, which is near 7.4. That is the around the pH of the plasma. So it provides buffering capacity of the intracellular environment. Hemoglobin, which is also quite amount that is 13.63%, provides buffering power in the mainly the RBCs. Now, what are the key points for the buffers? So they act immediately within seconds. They are first line orbital with the dates and pH, and they will only withdraw the acid and base. There is no final elimination of acid or base except the carbonic acid. So let's see the next mechanism which the body uses to control the pH. That is all the respiratory controls. Now the respiratory system acts within minutes, and it tries to control the volatile acid, that is the carbon dioxide, and further carbonic acid, and keeps the pH in control. So now the respiratory rate is indirectly proportional to the pH of the plasma. As the concentration of carbon dioxide increases, there is corresponding fall in the pH of the plasma because the hydrogen ion concentration is increasing. So this will stimulate the central chemoreceptors in the medulla of the lung, and that will increase the respiratory rate. So as the pH, that is the hydrogen ion concentration increases, there is no pH that will stimulate the respiration. Similarly, high pH, that is alkalosis, will inhibit the respiration. All these reactions are obviously following the law of mass action in the background, and according to which, in a reversible reaction, the concentration of reactants on either side of the equation determines the direction of the reaction. For example, if the carbon dioxide concentration increases on one side of the reaction, so this will direct the movement of the equation of the reaction of the forward side, on the forward side. So, and this will generate more carbonic acid, and this will decrease the pH, and that will stimulate the respiratory centers. Or if there is decrease in the bicarbonic acid concentration due to any reason, that will again the, make the reaction to move in the forward direction, and vice versa for the other situations. And when the rate of reaction is equal on both sides, that means the concentration are same on both the side of the reaction, and then the reaction is in dynamic equilibrium. Now, this slide shows how the respiratory control try to respiratory centers will try to control the carbon dioxide and carbonic acid concentration of the equation to maintain the system. So, on this side, uh, normal rate of activation, we will have a carbonic acid concentration of around 10.2 milligram per liter with a pH of 7.4 and carbonate concentration of 24 milligram per liter. And so they are in the ratio 1 is 1 e. The renal system will control the bicarbonate component of the equation. Now, if we bring the Henderson-Hasselbalch equation of the the picture, we will see that the respiratory system controls the carbonic acid, and the renal system controls the bicarbonate. The renal system controls the bicarbonate, and respiratory system controls the carbonic acid. Uh, in the equation to give the created the homeostasis. Now we will see the renal regulation of pH. As we have seen, there are three ways to control pH in the normal range. The renal system acts within days and try to buffer the fixed acids like lactate, acetoacetate, sulfate, phosphate, etc. to control the pH. So the kidney will take a little bit longer time and will act over days. And in general, the kidney acts by reabsorbing the filtered bicarbonate, synthesizing new bicarbonate, or excreting hydrogen and ammonium ions to regulate the pH. Now, as we all know that the urine formation process used by the kidney has three phases. Number one, that is non-selective filtration, then absorption, and then secretion. So, in non-selective filtration, most of the substance which affect the pH of the body fluids are non-selectively filtered in the proximal tubules of the kidneys. So these are, for example, hydrogen ion, bicarbonate ion, carbon dioxide, monohydrogen phosphate, dihydrogen phosphate, and other fixed acids. So let's see how the kidney will respond in situation when there is increase in base or the pH rises in the body. So what will happen that in such situation, the kidney will try to eliminate more bicarbonate than normal. and try to retain the hydrogen ion. Now, which will eventually increase the acid in the body, and therefore the pH will come in the normal range over few days. And in situation where the acid increases in the body fluids, kidney will try to preserve this bicarbonate rather than eliminating it. So there will be reabsorption of bicarbonate, generation of new bicarbonate, other than in addition to preserving the filtered bicarbonate. And also there will be secretion of acid, for example, hydrogen in the form of ammonium and H2PO4. So all these uh, processes will try to bring the pH back to the normal range. And now let's see how the kidney will try to conserve the bicarbonate ion in the PCT. So when the carbon dioxide levels are rising in all the tissues, carbon dioxide is more. So the environment is acidic. So the carbon dioxide will move into the PCT cell. So it will absorb the PCT cell as one of the tubular cells of the kidney. And so because of this rising metabolic reaction, carbon dioxide shown in this green color is increased in the PCT cells. So now the dioxide level has increased in the cells, and so the kidney will try to conserve the bicarbonate. Let's see which mechanism. So within the PCT cell, the carbon dioxide will react with the water and will form the bicarbonic acid. So this reaction is uh, done by carbonic anhydrase, and the carbonic acid will be formed. This carbonic acid will split into bicarbonate and hydrogen ion, and the hydrogen ion will move into the filtrate. So the hydrogen ion will move into the filtrate, then exchange for the sodium through this anti-port transport protein, anti-port transport protein. Sodium will be exchanged for the hydrogen. The hydrogen ion will be used with the filtrate, and sodium will be absorbed. So this absorbed sodium ion goes back to the plasma in exchange of protection with sodium pressure. And the bicarbonate has already been absorbed via the ion channel in exchange of chloride in the plasma. So at the end, the sodium bicarbonate is dissolved in the plasma. Now, in the filtrate, the hydrogen ion which has went into the filtrate will combine with the filtered bicarbonate, and it will form the carbonic acid. This carbonic acid will split into hydrogen ion. This carbonic acid will be converted into carbon dioxide and water. Now, this carbon dioxide will diffuse into the kidney tubular cells, and thus removing the bicarbonate from the filtrate. So as you know, as the filter, bicarbonate cannot move into the cell. So it must be moved as carbon dioxide. And when the carbon dioxide comes into the cell, the same process repeats, and the bicarbonate and sodium will be absorbed into the system. So in this manner, much of the filtered bicarbonate is reabsorbed by the kidney, and also the water generated will also be absorbed back. So this slide is showing how the bicarbonate is absorbed back to the plasma. So both bicarbonate and sodium are reabsorbed back to the plasma and the kidney, sodium and bicarbonate. So to summarize the result of this process, 80 to 90% of the filtered bicarbonate is reabsorbed back in the city, and more sodium is also absorbed as well. Now let's see how the kidney helps in generation of new bicarbonate ion uh, and iodine secretion. So it usually occurs when there is severe metabolic acidosis. It involves two processes which are coupled, which occurs in the late distal convoluted tubule and common collecting the cells of the kidney tubule. Now here the cells can generate the blue bicarbonate ion and secrete the hydrogen ion. First, let's see the generation of new bicarbonate ion. Now here the carbon dioxide present in the TCP cells reacts with the uh, reacts with the water to form carbonic acid in the presence of carbonic anhydrase. And after that, this carbonic acid splits into bicarbonate and hydrogen ion, and this hydrogen ion is secreted into a filtrate through hydrogen pump, similar to the PCT. But here the situation is something different. In the DCT, the bicarbonate levels in the filtrates is very less. So, is very less. So what will happen? They will release hydrogen ion. So the released hydrogen ion will combine with the hydrogen phosphate. Hydrogen phosphate will form dihydrogen phosphate. So this is a urinary buffer. So, uh, so the resulting dihydrogen phosphate will be unable to go back to the cell and will be trapped in the filtrate and is excreted in the urine ultimately. So this buffer will try to keep the pH above 4.5. So this slide is summarizing the about reaction. In the recycle cell, carbon dioxide or water in the presence of carbonic anhydrase or carbonic acid, which splits into hydrogen and bicarbonate. Bicarbonate goes back to the plasma. Hydrogen is secreted by the hydrogen pump into the tubular lumen, which combines with the hydrogen phosphate to form dihydrogen phosphate, which is ultimately released with the urine. Now, it is important to know that the hydrogen ion secretion will stop if the pH goes below 4.5. So this is because all the monohydrogen phosphate has been exhausted and the increase of hydrogen ion concentration left in the tubule is left unbuffered. So the hydrogen ion concentration will stop if the pH goes to about 4.5. So the result of this process is that the newly generated bicarbonate is added to the plasma and hydrogen ion is secreted down to the buffer that is monohydrogen phosphate that is eliminated with the urine. Now, in severe cases of acidosis, another process will occur in the cells of the PCT. So there is a amino acid known as glutamine. So in the PCT cell, we have a amino acid known as glutamine. So this glutamine is metabolized in the tubular cells. It is PCT cells to produce ammonia and bicarbonate. Now, the ammonia is exchanged with sodium from the filtrate to using the anti co-transport protein. Cycle co-transport protein, ammonia goes into the filtrate, sodium is exchanged into the PCT cell. So the ammonia, which is released in the filtrate, combined with the hydrogen ion to form ammonium ion, which is released into the urine ultimately. The sodium which enters into the cell is absorbed back into the system via sodium potassium pump. The potassium is exchanged for the sodium and bicarbonate for the chloride via the ion channels, and sodium bicarbonate is added to the system. So potassium comes in, sodium goes to the plasma, and bicarbonate is exchanged for the chloride. So sodium bicarbonate is added to the system. So to summarize the renal control of acidosis, it helps to reabsorb the secreted bicarbonate generate more bicarbonate in the TCP, hormone collecting duct, and PCT, adding to the full capacity of the plasma. Secreted hydrogen ions, they are in the form of dihydrogen phosphate and ammonium ions, are ready to overfiltrate and ultimately fill the urine. So to summarize, finally, we've seen how the pH homeostasis is maintained in the body, combined efforts of chemical buffers, acts over seconds, respiratory system, which acts over minutes, and try to eliminate volatile acid like carbon dioxide, carbonic acid, and renal system, which acts over days to eliminate fixed acids like lactic acid, keto acid, sulfates, phosphates, etc. So this was the respiratory control equation where showing the normal rate of ventilation, and the carbonic acid part is controlled by is under the respiratory control, and bicarbonate is under the renal control. And they are usually in the ratio of 1:10. So this is the Henderson-Hasselbalch equation where the salt, that is the bicarbonate, is regulated by the kidney, and carbon dioxide, which is the acid component, is usually regulated by the lungs in a combined effort to control the pH of the system. These are some of the references I have used so for this presentation, which you may find useful for your further study. I hope you have learned something new today, and you may find this presentation useful. Thank you for your time, and thanks.